One of the applications of integrals is that we can find the volume of solids that we create by rotating a function around an axis. And so this allows us to find the volume of shapes that before now we never would have even thought to take and find the volume of, at least not mathematically. And we could have, put it in water and looked at its density or whatever you do over there in those science classes. But as far as mathematically calculating volume, this will allow us to say, well, as long as I can create a function to model like a side basically of my solid, then I can use this formula and figure out what the volume is. Let's take a look at how we even go about this. So here's a graph of y equals square root of x. We're going to rotate it around the x-axis. So we're going to rotate it around to where it's like reflecting around the x-axis, but instead of just reflecting, we're actually taking it and thinking three-dimensionally about it going all the way around. Now this might be difficult to think about at first, so I'm going to show you some things to hopefully help you out. That the first thing you can do is just start by reflecting it over the x-axis, and then we're thinking of it three-dimensionally. So in each of these places it like comes out of our screen and creates a three-dimensional object kind of thing. I feel like this is a terrible job that I'm doing, but don't worry, because we have a better picture right here that's what it's supposed to look like. So if you can kind of say, okay, this is what it originally looked like. So that function that we're starting off with, the square root function, is this right here, basically. And so we've just taken that and we've rotated it around the middle. If you can think about it like there's a middle of that sticking out through the solid. We're just taking it and rotating it around and saying, okay, what's inside of this is the volume. Now, to actually find the volume, we're going to have to limit how far we go. Like, we can't just find the volume infinitely, or that would be an infinite volume, so that's boring. So we're going to have boundaries so that we only are finding so far on our graph. And once you get the hang of thinking of this like a three-dimensional solid, that'll be helpful. But in reality, we're going to use a formula. So even if you're not super great at thinking about this three-dimensionally, as long as you can use the formula, then you'll be fine. On this formula, we are going to use the idea that volume is our area over a height. If you think about like cylinders, when you did the volume back in the day, it's a really good cylinder, you do pi r squared h. The pi r squared part is the area of the top or bottom, then h is our height. What this formula is telling us to do is it's saying find the area of the base, and then because we're integrating, so the part on either side is going to end up giving us multiplying by the height. So it's kind of weird to think about, but that's where that formula comes from. But a of x is going to have to be some function, and it has to do with how we find the area of what's on our graph. And so if we look back at this and we look at this side here and we think about cutting off like the edge of this, what would the cross section of that, what shape would it be? And so a cross section is where you cut something and look at what it would be in a place that you normally don't see. Like if you do, I guess it's not necessarily something you don't see, but like a cross section of an orange would be circular because you cut an orange and it looks like a circle. On this as well, we're going to have something that looks like a circle. It kind of looks elliptical the way it is right now, but that's because of the attempt to make it a 3D perspective. So if our areas of the side of this, if we think about cutting off the end and then cutting off again and so on, if those are circles, we're going to use the formula for a circle, which is pi r squared, and that's going to give us our a of x. Well, so what happens is that the pi can be just outside instead of it being inside, cluttered with other things. And our radius is going to be squared. Our radius comes from our function. So let's look back again. Our radius for this figure here is different than it is here. Because if I cut it here, my circle is going to be, this big. But if I cut it over here, my circle should be this big. So the way that we account for our radius changing like that is our radius is the value of our function. So This second formula is what we'll need for the process of finding volume with disks. Disks is in circles. And so we're just going to use this formula and figure out what our answer is. Let's look at this example. This actually uses the same graph that I used up above, square root of x. On these examples, we're going to find the volume that results when the region enclosed by the curve is revolved about the x-axis. And then we're gonna use the graph here to help us visualize what's going on. So square root of x starts at 0, 0, and then goes to 1, 1, and then 4, 2, and we can make it go farther if we want. Well, actually it won't fit on this graph if we wanted to do another point, but it keeps going up and to the right. The other thing on here is it says y equals 0, which is the x-axis. Remember, y is a horizontal line because it's saying that y is always 0 and x can be whatever it wants. Oops. Then it says x equals 4, so that's a vertical line at 4. And what that means is that we're not going to keep going past 4, we're just going to look at this smaller part of our shape that we're going to get. So whenever we think about this as a three-dimensional solid, you don't have to draw the rest of it if you can think of it visually in your head, but it's kind of neat to look at. If I draw the rest of this down here, if I want to make this look three-dimensional, then I can just draw a circle at the end, and then like it's just going around like this. That doesn't look super great. Hopefully yours looks better. I believe in you. You can do it. All we really need from this, though, we don't really need to go into that much detail, is we need to fill in our formula. So volume equals pi times the integral from a to b. So this is going to be where our function started, which was over here at 0, and where it's stopping because of what they told us, 4. So we're going to do the integral from 0 to 4 of f of x squared. Well, this doesn't say f of x, it says y, but that's our function we're rotating. So we're going to do the square root of x squared. What's neat about that is the square root of x squared is just x. So this is pi, the integral from 0 to 4 of x dx, which, not that the square root of x is that bad to integrate, but this is easier. This pi is just going to hang out outside until the very end of our problem. We're not going to worry about it until then. We're going to power rule x. So we get x squared over 2. And we're going to put in 4 and 0. Then when we plug those in, we do 4 squared over 2 minus 0 squared over 2. Or if you just wrote 0 or nothing at all, that's fine. 4 squared over 2 is 8. 8 minus 0 is just 8. So now the pi comes in, we're going to do 8 and pi together as 8 pi. And so because all of these are multiplied by pi, because what we're looking at are circles on the end, we will always end up with a pi in our answer. Very rarely is there a reason for you to actually type into your calculator 8 times pi and write the decimal, whenever you can just figure out what it is without pi and then put pi next to it. So that's our best answer, is 8 pi. So let's try some more. How about y equals 1 over x? We've got a line at y equals 0. So, in fact, I think all of these examples, because on all of these examples today, we are rotating about the x-axis as opposed to the y-axis or some line other than the x-axis. And so it's going to have y equals 0 as one of them. We have x equals 1/5, which is over here, and we have x equals 2, which is right here. Those are giving us our bounds. Like, without us even really having to do anything, we can know that our bounds are 1/5 and 2. And before you get super annoyed about it being a 1/5, here's why. When we graph this function, nothing is happening at x equals 0. I have a point at 1, 1, and then it goes down to the right towards 0 and up to the left towards the y-axis, but it never actually touches 0, and so that's why they couldn't just say x equals 0. So what we're doing is we're basically cutting off our graph on the left fairly close to 0, and then over here at 2. So we've just got this like little sliver that we're going to rotate around. And if you want to, you can try to think about what that shape would look like. It would kind of look like a funnel or part of a tornado or something on its side, in case you're like, I don't know where you're getting that. It'd look like this part is big, but then it goes down really fast and up really fast, so that we've got a funnel looking thing. Now, we need a pi in front. We need our function, which is 1 over x, to be squared. If 1 over x is squared, that's the same as saying 1 over x squared. And since it's 1 over x squared, to integrate this, we'll want to move that up to the top and then add a power and divide. And so that's going to give us x to the -1 divided by -1. But we're going to rewrite it with the x on the bottom. So minus 1 over x. We'll plug in 2 1/5 times by pi, and that'll be our answer. And remember, you plug in the top number first. So we have -1 over 2 minus, but then we have a negative from our problem. So we're going to make it a plus. We're going to do 1 over 1/5. So 1 over 1/5, when we divide by fractions, we flip the second fraction and multiply. So 1 over 1/5 ends up being 5. So we just need to figure out what -1/2 plus 5 is, which is 4.5. But if we want to write that as an improper fraction, that would be 9/2. Since we're timesing by pi, that'll be 9/2 pi. This graph is a cubed root function, which you may not be super familiar with. It kind of looks like a square root function, but instead of only going up and to the right from 0, 0, it goes both directions, because you are allowed to put negatives into a cube root. They give you negative answers. So we actually, I don't want to do 9, I want to do 8, because you can cube root 8. That was my bad. But we want to graph this. So if you're plugging into your calculator to graph this, you have to use the math menu on the TII calculators. You go to math, and it's either the third or the fourth option. I'm not sure which off the top of my head, but one of the options says cubed root, the next option says whatever root, like you can put in any root you want to. So you can just use the one that says third root, you don't have to use the other one. We get points like 0, 0 and 1, 1. Then the next point that we can do that's not a decimal is actually 8, because the cubed root of 8 is 2. And that's part of why we want to use 8 as our bound. As if we wanted nice boundaries, we would have had to use 8 or 1 or -1 or -8. So here's my cubic function. It also cubed root function. It also looks like a cubic function on its side, like this. Then we can draw these other two lines, like y equals 0 is the x-axis, and that just means that will be between the x-axis and our curve. Then we're going to do x equals 8, so that's a vertical line over here on the right side of our graph that tells us where to stop. So if we want to shade the place that's enclosed here by these three functions, that's this part over here on the right. If they hadn't given us the y equals 0 boundary, this would have been weird. It might have been that we would have had both sides, or we'd have to figure out what to do in that case, but they did give us the x-axis as a boundary. So if we reflect this, what's happening is it comes down this way, and then if you imagine the edge of this as a circle, it's going to look really similar to the way our square root function looked like. It won't go up as fast. It goes right really fast, but it doesn't go up as fast as our square root function did. If we want to find the volume of this, we're going to use that formula, pi integral from The boundaries here are 0 and 8 because over here we're intersecting at 0 with the x-axis, and then they basically told us to stop at 8. We're going to do the cube root of x squared, and that's the integral we're going to take. Now this requires us to remember some things from like algebra 2 or algebra 1. The way we rewrite the cube root of x squared with a rational exponent, with a fraction as an exponent, is that the root goes on the bottom of our fraction and the power goes on top. So the part of this that is the root is the 3. So this will be x to the something over 3. The power we have is 2, so that's what goes on top. This is the same as saying x to the 2/3. And if we use x to the 2/3, we'll be able to use the power rule to integrate this. So if I want to add a power to 2/3, I need a common denominator of 3. So I'm going to add 3/3. And that gives me, I don't need that integral symbol anymore. That gives me 5/3. And I have to divide by 5/3. We'll plug in 8 and 0. And depending on whether or not you're going to use your calculator for this or not, either way it's actually pretty easy as long as you know what we're doing. This 5/3 on the bottom, when we rewrite it, will be 3/5 not on the bottom of our fraction. To get it off the bottom, we use the reciprocal. Or you can think of it like we've basically got x to the 5/3 and we're timesing it by its reciprocal. Because we were dividing by 5/3, we times it by 3/5. If we think of x to the 5/3 as being the cube root, again, with a power of 5, this will be really easy for us to figure out by hand, actually, because we can cube root 8 and we can cube root 0, and then we find the 5th power of whatever it is. So this first part, 3/5 cube root of 8 to the 5th power. Then we're going to subtract the cube root of 0 is 0, so that part will be 0. This is 2. 2 to the 5th power is 32. And so we're going to do pi times 3/5 times, that made it look like divide by 2. That part is 2. We're going to do 2 to the 5th, which is 32. So we're doing pi times 3/5 times 32, which ends up being 160/3 pi. So there's that one. Compared to these first 3 graphs, this next graph should look a little bit more normal to start off with, because we're going to do a parabola, x squared plus 1. We have boundaries of y equals 0 and x equals -1 and x equals +2. So the x-axis is one of our boundaries. -1 is a boundary, and +2 is a boundary. So we just need to graph our parabola. This is pretty easy to graph by hand if you want to. If you use your calculator, that's fine too. But it starts at 1 on the y-axis, and then it is a normal parabola x squared. So that means it goes up 1 and over 1, both directions. Then it goes up 3 more to get up here to 5. And you can plug in numbers to figure this out as well. So this is our parabola. If I want to rotate the region that's between all of these curves, that is the region underneath the parabola, but inside of the boundaries. So this part inside of here. We are rotating this around the x-axis. And so that means we would take this graph and we would think of it like we're putting it over here on the other side. And then imagine that we make this 3-dimensional. Let me use a different color than the one I already used. So the edge of it, or this side of it, would look like this, kind of. And so it kind of looks like I don't know what it's called. I don't know, but it's something like if you imagine it being on its side, it kind of looks like something. You know what I'm talking about, right? It looks like that thing that everybody knows about. So anyway, let's do this math now. We're going to use our volume formula. Volume equals pi times the integral. They gave us our boundaries, -1 and 2. And then we have our function, which is x squared plus 1 squared dx. Now, this function is something we're like actually pretty used to. The easiest function to do volume on is a square root function, since squaring it just makes the square root go away. If I want to square x squared plus 1, I need to think about that like it is x squared plus 1 times x squared plus 1. And FOIL, if you just say that this is x to the 4th plus 1 because you square each term, well, that's part of it, but there's a middle term that we get from doing x squared times 1 plus x squared times 1, which is 2x squared. So make sure that you actually think through the process of foiling there so that you don't forget that middle term. Now we can just use the power rule. So we're going to add a power and divide. So we get x to the 5th over 5 plus 2x cubed over 3 plus 1x. And we're going to put in 2 and -1. So this may not be super pleasant to work out because we're going to end up with fractions. So this might be one that we just want to put in our calculator if we have that as an option. We'll need to be careful on this second part that we put these -1s in parentheses and we don't change any signs before we put it in. So at this point, we can either put this in our calculator or work on doing it by hand, whichever one is your preference. If we're working it out by hand, we should end up with this being 32/5 and 16/3 plus 2 minus, this should be -1/5, -2/3 minus 1. And so even at this point, it's like, maybe I would rather do this in the calculator, except that we do have common denominators across our parentheses. So if I distribute my negative to the second one and then add like terms, so if I change all these signs, we'll have 32/5 and 1/5, which is 33/5. 16/3 and 2/3 add together to get 18/3, which is really 6, and then 2 plus 1 will be +3. So we have 9 plus 33/5, and so either by getting a common denominator or by plugging that into our calculator, we should end up with 78 pi over 5 for our answer.